Have you ever looked at a line of Python code and just thought, wow, that's really clever? Well, today, we're going to pull back the curtain on that magic. We're not just here to solve problems, we're going to explore the beautiful, elegant thinking behind some of Python's best solutions. We're going to take on 3 classic programming puzzles. And you've probably seen these before, right? They pop up in coding interviews, in practice exercises, and they are just perfect for showing off what makes Python, well, Python. But here's the fun part. For each of these problems, Python has a solution that is so clean, so intuitive, it honestly feels less like you're writing code and more like you're performing a magic trick. Okay, let's kick things off with a real classic, reversing the words in a sentence. This is where we get to see Python's first superpower, and it's this incredible, almost effortless ability to manipulate text.
So the goal is pretty simple. You take a string like Python is awesome, and you want to flip it into awesome is Python. See that? The words are reversed, but the letters and the words themselves stay exactly the same.
So, the big question is, how do you do this without some big, messy, complicated loop? What's the Pythonic way to get this done? The process is just beautiful in its logic. First, you use the split.cop method to chop the sentence up into a list of individual words. Then, you reverse that list. And finally, you use .join to glue all those words back together with spaces in between. 3 simple, super powerful steps. And here it is. This is the heart of the trick. That little bit of syntax, slice, -1, is called list slicing. It is one of the most fantastic shortcuts in Python. It instantly creates a reverse copy of any sequence, whether it's a list of words or even the characters in a string. It's so concise, but it packs a serious punch.
All right, so for our second challenge, things get a little more interesting. We need to take all the zeros in a list and move them to the end. But, and this is a big but, we have to do it in place. This is where we really have to start thinking about memory and efficiency. Just take a look here. Our input is 0, 1, 0, 3, 12. And what we want to get is 1, 3, 12, 0, 0. Now pay close attention to this. The non-zero numbers, the 1, the 3, and the 12, they're still in the same relative order. That is a really important part of this puzzle.
So what does in place actually mean? Well, it means we're not allowed to just make a new empty list and start filling it up. Nope. We have to work with the original list, modifying it directly in memory. This is so important when you're dealing with huge amounts of data, where creating a copy would be a waste of resources.
This is where you have to get clever. How can we possibly shuffle these members around inside the list itself to get the final result we're looking for?
The answer is a really elegant algorithm known as the two-pointer approach. All we need is a single variable, we'll call it pause, that acts like a little bookmark. Its job is to keep track of the next open slot where a non-zero number should go.
Okay, let's just walk through this. At the very beginning, here's our list, 0, 1, 0, 3, 12. And our pause bookmark is sitting right at the start, at index 0, just waiting for the first non-zero number it finds.
So as we scan through the list, boom, we hit our first non-zero number, which is 1. We immediately move it to the spot marked by pause, which is index 0. Then, and this is the crucial part, we slide our pause bookmark 1 step forward. It's now at index 1, waiting for the next non-zero number.
So we keep doing that, and after we've scanned the entire list, all the non-zero numbers have been neatly shifted to the front. Our list now looks something like this: 1, 3, 12, 3, 12. And our little pause bookmark has stopped at index 3.
And you know what? The hard part's over. Now, all we have to do is clean up. We start a second, super simple loop right where our bookmark left off, at index 3. And we just fill in the rest of the list with zeros. And just like that, it's done. Perfectly sorted, all in place.
For our final puzzle, we're going to switch gears a little. Instead of rearranging data that already exists, we're going to build it from scratch. We're going to generate the famous Fibonacci sequence and see just how good Python is at creating data dynamically.
So the goal is to write a function that, if you give it a number, say 7, it returns a list with the first 7 Fibonacci numbers. In this case, that would be 0, 1, 1, 2, 3, 5, 8. And remember, each new number is just the sum of the 2 that came right before it.
The real logical trick here is that self-reference. I mean, think about it. To calculate the next number, you need to look at the last 2 numbers you just created. How does Python handle that so gracefully?
The approach is just beautifully simple. We kick things off by creating a list with the first two numbers, 0, 1. Then we loop n minus 2 more times, and inside that loop we calculate the next number by just adding the last two elements in our list. Then we use the handy .append method to stick that new number on the end, and we just keep going. And this, right here, reveals our third superpower, negative indexing. In Python, if you want the last item in a list, you just ask for list -1. If you want the second to last, it's list -2. This ridiculously simple feature makes the code for the Fibonacci sequence incredibly easy to read. It's just peak Python.
So, there we have it. We've just unpacked 3 really clever solutions. But actually, we've done more than that. We've just added 3 powerful new tools to your personal Python toolkit. Let's do a quick recap. For effortless text and list manipulation, you've got split, join, and that awesome slice one slice. For memory efficiency, you now have the 2-pointer technique in your back pocket. And for building data structures dynamically, you know how to use negative indexing and .append together.
You see, these aren't just one-off tricks. These are fundamental patterns for writing cleaner, faster, and just plain better Python code. They actually change the way you approach problems. So the only question left is, what puzzle are you going to solve with them next?
All right, let's talk Python. Today, we're not just about getting the code to run, we're on a hunt for something more. We're looking for elegance. We're going to tackle 3 common problems, but our goal isn't just to find an answer, it's to find the most clever, efficient, and truly Pythonic solution. See, anyone can write code that works, but what separates good code from great code is that aha moment. It's about finding that simple, powerful solution that just clicks. It's about thinking like a true Python pro. So, you ready to crack a few of these puzzles with me? Okay, first up is a real classic. We're trying to find the common ground between 2 different groups. You can think of it like this. Imagine you have 2 guest lists for a party. How do you quickly find out who was invited to both? So here's the specific challenge. We've got 2 lists of numbers. Now pay close attention. The first list has a duplicate number 2 in it. Our job is to find a clean list of numbers that show up in both of the original lists, but without any duplicates in our final answer. So for these 2 lists, the correct answer we're looking for is just 2, 3. Now, how do we solve this? Well, you could do it the brute force way. You know, take the first number from list 1 and check it against every single number in list 2. Then take the second number and do it all over again. It works, sure, but it is slow and clunky. But the elegant approach, it uses a secret weapon built right into Python that makes this whole thing ridiculously fast. And that secret weapon is the set. A set is a fantastic data structure in Python. It basically has 2 superpowers. First, it automatically, instantly gets rid of any duplicates you throw at it. Second, it's built for these kinds of lightning-fast comparisons, like finding the overlap between 2 groups. And here is that elegance in action. Look at this. We just convert both of our lists into sets. Boom, the duplicates are gone. Then we use a single character, the ampersand, to find the intersection. That's the stuff they have in common. We turn that result back into a list and we're done. 3 lines. It's clean, it's fast, and it is perfectly Pythonic. All right, puzzle number 2. We're shifting gears a little bit here, from clever data structures to a programming technique that can feel a little mind-bending at first. We're going to solve the puzzle of the factorial, and to do it, we'll use a function that actually calls itself. This idea is called recursion. The best way to think about it is like a set of Russian nesting dolls. You open the biggest doll, and what's inside? A slightly smaller version of itself. You keep opening smaller and smaller dolls until you get to that last tiny one that doesn't open. That little solid doll, that's your base case. It's the point where the process finally stops. And this is what it looks like in Python. The function calculates a factorial, let's say of 5, by returning 5 times the factorial of 4. That's the part where it calls itself. But, and this is the most important part, we have a safety net. The if n equals 1 part is our base case. That's our tiny, solid nesting doll. It stops the function from calling itself forever and causing a crash. So let's trace it out. If we call factorial of 5, it immediately calls factorial of 4. That one calls factorial of 3, and this goes on, diving deeper down the rabbit hole until we finally hit factorial of 1. Right there, it hits our base case and gets a real answer, 1. Now the magic happens. It starts to unwind. The answer 1 gets passed back up to the factorial of 2 call, which can now figure out it's 2 times 1. That 2 gets passed up to factorial of 3, which calculates 3 times 2 is 6. This bubbles all the way back up to the top, finally giving us our answer, 120. And for our final puzzle, let's hold a little competition. We're going to take a sentence and try to find the champion, the one word that stands out from all the others. But the real puzzle is, how do we decide who wins? How do we define our champion?
The challenge itself sounds pretty simple, right? Find the longest word in a sentence. I mean, we can look at the quick brown fox jumped and see that jumped is the winner. The real question is, how do we tell Python to judge these words by their length and not by, say, alphabetical order? Okay, check this out, because this is where a little bit of Python knowledge is like a superpower. On the left, if you just use the normal max function on a list of words, it defaults to alphabetical order, so quick wins just because it comes later in the alphabet. But look at the right. We add one simple argument, key equals lin. And just like that, we completely change the rules of the game. We're telling Max New, hey, ignore the alphabet. I want you to judge these words based on their length. And suddenly, Brown is our champion.
So what is this key argument? It is one of the most powerful, flexible tools in your Python toolbox. It's a way for you to give custom instructions to built-in functions like max, min, and sorted. It's like you're handing Python a custom-made measuring tape and saying, here, use this to decide what biggest means. And with that knowledge, the final solution is just beautiful. It's so clean. You split the sentence into a list of words, and then you just ask for the max of that list, telling it to use length as its key. That's it. One line of code does all the hard work of looping, checking lengths, keeping track of the longest, and giving you the final answer.
So if you've been following along, we haven't just solved 3 little puzzles. What we've actually done is add 3 incredibly powerful new tools to your personal coding toolkit. Let's do a quick recap of what you've just learned. So here they are, your 3 new secret weapons. First, you've got sets. Anytime you need to deal with unique items or find overlaps, sets are your go-to. Second, you've got recursion, this elegant way to solve big, scary problems by breaking them down into smaller, identical versions of themselves. And finally, you have the key argument, which lets you bend Python's most powerful functions to your will. And these aren't just for coding challenges. These are real-world tools. Just think about it. With that key argument, you could sort a list of products by price or find the customer with the most orders. The possibilities are endless. The question is, now that you have these tools, where are you going to use them?